Right, so in this video we're going to do example 3. We're going to evaluate this definite integral. I'm first going to just go through it, going through the motions so that we can get some traction with the steps that need to be taken to evaluate this integral. And then we're going to go ahead and think about the argument that's being made when we use fundamental theorem of calculus part 2, and I have an animation to kind of help us visualize the argument that's being made. But what fundamental theorem of calculus part 2 says, it's so nice. Instead of doing this, taking the limit of sums of areas of rectangles, heights times bases, and take a limit. Here we've got a finite number of rectangles whose area, height times base, we are adding up. And then we're going to take the limit as the number of rectangles goes to infinity. Instead of doing all that, which is yucky, fundamental theorem of calculus part 2 says we can ask ourselves a different question that has the same answer. So here we go. The function right here, we are going to come up with an antiderivative for that function. All right, so when I look at the green function that I've just highlighted here, I see that that function is composed of terms, one function of x minus another plus another. So I can compartmentalize my thinking and just come up with an antiderivative for 4x cubed first. Maybe that one's easy to see. If I take the derivative of x to the fourth, I get 4x cubed, check. But if you don't see that, you can go ahead and do your power rule in reverse. We're adding 1 to the exponent, 3 plus 1 is 4, and dividing by the new exponent. Minus 3 times x squared, we're going to do an antiderivative for that. I am going to add 1 to the exponent, x cubed, divide by the new exponent, 3, and then plus 6 times, doing power rule in reverse here as well, adding 1 to that exponent, we get x squared, and divide by the new exponent. Now instead of doing a plus c, we don't want that. We're not the question isn't to come up with the general antiderivative. We're just coming up with one antiderivative, and then fundamental theorem of calculus says that I'm going to go ahead and evaluate that at my endpoints. And a lot of times people will just do a like this gray big bracket that I've put in here and write a 1 and a 2, or even say we're going to evaluate this as x goes from 1 to 2. Just inched that down there. Sometimes people will just put one line right here and write as x goes from 1 to 2, or just 1 to 2. I think I'll put the whole bracket. And now we're going to plug in these endpoints. And here they are, right? That's an x is 1. And then here, that's where we're starting, and then stopping here at x is 2. All right? And so fundamental theorem of calculus says that I can just evaluate this antiderivative at these endpoints and take the difference. Order matters in subtraction, so I want to plug in the 2 for x first. Although, maybe let's actually go ahead and simplify in here. 4/4 is 1, 3/3 is 1, 6 divided by 2 is 3. Let's go ahead and simplify. We've got x to the 4th minus x cubed plus 6 divided by 2 is 3x squared. I just simplified green. And now I'm going to go ahead and evaluate these at the at the end points. X equals 1 and x equals 2. So you don't have to write the x. This is just maybe a little cleaner. Plugging in 2 first. We've got 2 to the 4th minus 2 cubed plus 3 times 2 squared. that's plugging in a 2 for an x, and then we're going to subtract plugging in the 1 for the x. 1 to the 4th minus 1 cubed, that's a minus sign, plus 3 times 1 squared. All right, I didn't need the parentheses or brackets here on the red one, but I absolutely did need them on the green because I am subtracting this whole thing, right? So I want to subtract each term, or we simplify within. 2 to the 4th is 2 times 2 is 4, times 2 is 8, times 2 is 16, minus 2 cubed is 8, plus 3 times 2 squared. 2 squared is 4, times 3 is 12, so there's that guy, minus, in the green, 1 to the 4th is 1, minus 1 cubed is 1, plus 3 times 1 squared is 3. Simplifying here, 16 minus 8 is 8, plus 12 is 20. Minus 1 minus 1 is 0, plus 3 is 3, so we're minusing a 3. And 20 minus 3 is 17. And we are done, but we need to know what the argument is. What have we found? All right, and then to do that, I want to look at this Desmos animation. So the signed area under my purple curve is given by this definite integral. This is what we were asked to find, right? Integrating from 1 all the way up to 2, right? And notice that the definite integral does equal 17. That is the area under this purple curve right here, which is the 4x cubed minus 3x squared plus 6x. And finding that area is really intense, right? This is what that takes. Heights of rectangles times bases of rectangles, add up a finite number of rectangles, and then take the limit as the number of rectangles goes to infinity. That's yucky. But because we can come up with an antiderivative for this function, let's see that on Desmos. Here, big capital F, that's the antiderivative that we found. Evaluating that at the endpoints, when b is 2 here on my slider and a is 1, notice that this height, I don't know if you can see my cursor right here, but I'm right on that dot. That height, that y value minus this y value, well, that is our 20 minus our 3. And 20 minus 3, that height, that length right there, is the same number as the area under that curve, right? So pretty slick. We are asking ourselves a totally different question. All right, here's a nice one that I filled out from a previous semester. It's just that Desmos illustration, but maybe it makes it a little bit clearer. The area under this purple curve, 4x cubed minus 3x squared plus 6, that area is hard to find. So what we do is we come up with an antiderivative for 4x cubed minus 3x squared plus 6. That's this green function right here. The antiderivative, or just any antiderivative for that matter. And the difference in these heights, when I plug in 2, big F of 2 is 20. When I plug in 1, big F of 1 is 3. That length right there is 17. That's the same number as this area. And that's what Fundamental Theorem of Calculus Part 2 leverages. It's so amazing. And I do want to say one last thing. It says we can come up with any antiderivative right here and then evaluate it at the endpoints. You don't need your plus c. But if you did put in a plus c or gave a specific number for what c is, notice you would be subtracting that off. If we had a plus c right here and then a plus c right there, c minus c is 0, right? So that's why they say, hey, just come up with any antiderivative for the function here, and go ahead and evaluate it at the endpoints, that length will always be that area. All right, I hope this video was helpful. We're going to do quite a few more.